Right now, as you're watching this video, you're hurtling through space at over 500,000 miles per hour. You're spinning, tumbling, and racing through the cosmic void on a journey so vast that your mind will struggle to comprehend its true scale. You're traveling aboard a tiny blue marble that orbits an ordinary star nestled within one of the spiral arms of an absolutely colossal structure called the Milky Way galaxy. But here's what should make your brain tingle with wonder. Despite living inside this cosmic behemoth our entire lives, despite it being our home for the entirety of human existence, we've only recently begun to grasp just how monumentally massive our galactic neighborhood truly is. Before we dive into this cosmic adventure together, I'd love to know where in the universe you're tuning in from tonight. Drop a comment and let me know what time it is in your corner of our pale blue dot. And if you find yourself drawn to these explorations of cosmic scale and wonder, I'd be incredibly grateful if you subscribe to join our growing community of cosmic explorers. Get ready. The journey begins now. Tonight, we're embarking on a journey to understand the true scale of our cosmic home. We're going to explore a structure so mind-bendingly enormous that light itself, racing at 186,000 miles per second, takes over 100,000 years to cross from one side to the other. We're going to discover how astronomers solved one of the most challenging puzzles in science, measuring the size of something when you're trapped inside it. This is the story of humanity's greatest measurement challenge. Imagine trying to determine the size of a vast city while being blindfolded and placed somewhere within its boundaries. You can't see the edges, you can't fly above it for perspective, and you're limited to making observations from your fixed position on the ground. That's essentially the challenge astronomers have faced for centuries in trying to understand the true scale of the Milky Way galaxy. But by the time we're finished tonight, you'll understand not just how big our galaxy is, but how that measurement revolutionized our understanding of our place in the cosmos. You'll discover that the Milky Way isn't just big, it's so incomprehensibly vast that it contains somewhere between 100 and 400 billion stars, each potentially hosting its own family of worlds. The journey to understand our galactic home begins thousands of years ago, long before telescopes, long before we even knew what a galaxy was. Picture ancient civilizations looking up at the night sky and seeing that ghostly band of light stretching across the heavens. They had no idea they were looking at the combined glow of billions upon billions of distant suns, all part of the same colossal structure that contained their own world. The ancient Greeks called it Galaxias Kyklos, meaning the Milky Circle. Other cultures saw it differently. Some Native American tribes called it the Trail of Spirits, believing it was the path souls took to the afterlife. The ancient Chinese referred to it as the Silver River of Heaven. But despite these poetic names, no one understood what they were actually seeing. For millennia, that faint river of light remained one of the universe's greatest mysteries. Was it some kind of celestial cloud, a cosmic river, the breath of gods? The truth would prove far more extraordinary than any myth or legend could have imagined. The first breakthrough came in 1610 when Galileo Galilei turned his primitive telescope toward the Milky Way. What he discovered changed everything. That ghostly band of light wasn't a cloud or a river. It was composed of countless individual stars, so distant and numerous that they blurred together into a continuous glow when viewed with the naked eye. But even Galileo's revolutionary observation only scratched the surface of the mystery. If the Milky Way was made of stars, how many stars were there? How far did it extend? And perhaps most puzzling of all, what was our sun's relationship to this vast stellar collection? The quest to answer these questions would consume the next 3 centuries of astronomical research. Each generation of astronomers would push the boundaries of our understanding a little further, revealing layer after layer of cosmic complexity that previous generations couldn't have imagined. One of the first serious attempts to map our stellar neighbourhood came from William Herschel in 1785. Herschel, the same astronomer who discovered Uranus, embarked on an ambitious project to understand the shape and size of what we now call the Milky Way galaxy. His method was elegantly simple. He would count stars in different directions across the sky. Herschel's reasoning was straightforward. If he looked in one direction and saw many stars, that probably meant the Milky Way extended farther in that direction. If he looked another way and saw fewer stars, the galaxy's edge might be closer. By systematically counting stars across the entire sky, he could map out the rough shape and size of our stellar system. What Herschel discovered was revolutionary for its time. The Milky Way wasn't spherical like the planets. It was flattened, like a disk or wheel, and it was much larger than anyone had previously imagined. Most surprisingly, Herschel's star count suggested that our Sun was located near the centre of this vast stellar disk. This seemed to place humanity in a cosmically privileged position. We weren't just inhabitants of any random world orbiting any ordinary star. We appeared to live near the very heart of the entire universe of stars. It was a conclusion that fit perfectly with the anthropocentric worldview that had dominated human thinking for millennia. But Herschel's measurements, groundbreaking as they were, suffered from a fundamental problem that wouldn't be understood for more than a century. His star counts were being systematically distorted by something invisible, something that absorbed and scattered starlight as it travelled through space. What Herschel couldn't see was that space isn't empty. It's filled with vast clouds of dust and gas that act like cosmic fog, dimming the light from distant stars and making them harder to detect. This interstellar dust would prove to be one of the greatest obstacles to understanding our galaxy's true size. Just as earthly fog can make a forest seem smaller than it actually is by hiding the most distant trees, cosmic dust made the Milky Way appear smaller and placed us artificially near its centre. The next major advance came from a Dutch astronomer named Jacobus Kapteyn in the early 1900s. Kapteyn refined Herschel's star-counting approach, using improved telescopes and photographic techniques to survey stellar positions and brightnesses across the sky. His work produced what became known as the Kapteyn universe, a model of our galaxy that was more sophisticated than anything that had come before. According to Kapteyn's measurements, the Milky Way was a relatively small elliptical collection of stars, about 15,000 parsecs in diameter. For context, a parsec is roughly 3.26 light-years. So Kapteyn was suggesting our galaxy spanned about 50,000 light-years from edge to edge. Like Herschel before him, Kapteyn's analysis placed the Sun near the centre of this stellar system. But even as Kapteyn was refining his model, another astronomer was preparing to shatter our understanding of cosmic scale entirely. His name was Harlow Shapley, and his approach to measuring the galaxy would prove far more revolutionary than simple star counting. Shapley focused his attention on mysterious objects called globular clusters. These are dense spherical collections of ancient stars that orbit around the Milky Way like satellites around a planet. What made globular clusters particularly useful for Shapley's purposes was that they could be seen at enormous distances, far beyond the reach of individual star surveys. Using the 60-inch telescope at Mount Wilson Observatory, Shapley began a systematic study of globular clusters throughout the sky. What he discovered would revolutionize our understanding of our place in the cosmos. The globular clusters weren't distributed evenly around the sky as you might expect if the Sun were at the galaxy's center. Instead, they were heavily concentrated in one direction, toward the constellation Sagittarius. Shapley's interpretation was bold and ultimately correct. The globular clusters weren't randomly distributed. They formed a roughly spherical halo around the true center of the Milky Way galaxy. The fact that they appeared concentrated in one direction meant that we weren't at the center of the galaxy at all. We were displaced, located in what we would now call the galactic suburbs, roughly 30,000 light-years away from the true galactic center. This was a profound demotion for humanity's cosmic status. We weren't at the center of the universe. We weren't even at the center of our own galaxy. We occupied a distinctly off-center position in what Shapley determined was a much larger stellar system than anyone had previously imagined. Shapley's measurements suggested the Milky Way was roughly 100,000 light-years in diameter, making it nearly twice as large as Kapteyn's estimates. But even more revolutionary was the implication that our Sun was just one ordinary star among hundreds of billions, located in an unremarkable region of galactic space. The 1917 publication of Shapley's results marked a turning point in our understanding of cosmic scale. For the first time, humans had a reasonably accurate picture of their galactic home's true size and their position within it. But Shapley's work also raised new questions that would drive astronomical research for decades to come. If the Milky Way was this enormous collection of stars, what lay beyond its edges? Were there other such stellar systems scattered through space? And how could astronomers continue to refine their understanding of galactic structure while trapped within the very system they were trying to measure? The answers to these questions would require new technologies, new observational techniques, and new ways of thinking about the cosmos. The story of measuring the Milky Way was just beginning, and the most surprising discoveries still lay ahead. In the 1930s, a crucial piece of the puzzle fell into place when astronomer Robert Julius Trumpler solved the mystery that had been plaguing galactic measurements since Herschel's time. Trumpler was studying open star clusters, groups of young stars that form together and travel through space as a unit. By analysing the colours and brightnesses of stars in these clusters, he made a startling discovery. The most distant clusters appeared redder than they should have based on the types of stars they contained. This reddening effect was exactly what you'd expect if starlight was being filtered through dust as it travelled through space. Trumpler had quantified the effect of interstellar dust absorption, the invisible factor that had been distorting galactic measurements for centuries. This discovery revolutionized galactic astronomy. Once astronomers could account for dust absorption, they could correct their distance measurements and get a clearer picture of the galaxy's true structure. The Milky Way began to emerge from the cosmic fog, revealing its actual scale and organization. With dust effects properly understood, the modern picture of the Milky Way finally began to take shape. Our galaxy was indeed a vast, flattened disk of stars, roughly 100,000 light-years in diameter. But it wasn't just a simple disk. It had complex structure, a central bulge of older stars, spiral arms where new stars were being born, and an extended halo of globular clusters and dark matter reaching far beyond the visible stellar disk. But measuring the Milky Way's size from our embedded position within it remained an enormous challenge. Imagine trying to map the layout of a vast forest while standing somewhere among the trees. You can see nearby trees clearly, but distant ones become harder and harder to make out. Eventually, you reach a distance where individual trees become impossible to distinguish from the general forest background. Astronomers face exactly this problem when studying our galaxy. They can measure distances to nearby stars with great precision using a technique called parallax, which relies on the apparent shift in a star's position as Earth orbits the Sun. But parallax only works for relatively nearby stars. Beyond a few thousand light-years, the shifts become too small to measure accurately, even with our best instruments. For more distant objects, astronomers must rely on what they call standard candles, objects whose true brightness is known or can be calculated. By comparing an object's apparent brightness as seen from Earth with its known far away it must true brightness, they can determine how B. The dimmer it appears, the more distant it is. But finding reliable standard candles throughout the galaxy is challenging. Different types of stars have different intrinsic brightnesses, and those brightnesses can change over time as stars age and evolve. Dust absorption affects different wavelengths of light differently. making distance calculations even more complex. Despite these challenges, generations of astronomers have gradually built up a detailed map of our galactic neighborhood. They've identified the major spiral arms, traced the distribution of gas and dust, and mapped the locations of star-forming regions throughout the galactic disk. What they discovered using these painstaking methods would reshape our understanding of cosmic scale forever. As more sophisticated instruments came online and observational techniques improved, a picture emerged of a galaxy far more complex and vast than anyone had dared imagine. The breakthrough that truly revolutionized our understanding came with the development of radio astronomy in the mid-20th century. Unlike visible light, radio waves can penetrate the dust clouds that had been obscuring astronomers' view of distant galactic regions. For the first time, scientists could peer through the cosmic fog and map the true extent of our stellar home. Radio telescopes revealed something extraordinary. The Milky Way wasn't just a collection of stars scattered through space. It had elegant, sweeping structure. Vast spiral arms emerged from the data, graceful curves of stars, gas and dust that wound outward from the galaxy's center like water spiraling down a cosmic drain. These spiral arms told a story of ongoing creation. They weren't just static features, but dynamic regions where interstellar gas was being compressed and heated, triggering the birth of new stars. The radio observations showed that star formation was happening continuously throughout the galaxy, with each spiral arm serving as a stellar nursery where the next generation of suns was coming to life. But perhaps the most startling discovery was just how much of the galaxy had been hidden from optical observations. The radio maps revealed that the Milky Way extended much farther than visible light surveys had suggested. What astronomers had thought were the outer edges of the galaxy were actually just the limits of what they could see through the dust. As radio astronomy matured, it became clear that our galaxy was truly enormous. The visible disk that had been mapped by generations of optical astronomers was just the bright center of a much larger structure. Radio observations pushed the known boundaries of the Milky Way outward, revealing a galaxy that was significantly more massive and extensive than previous measurements had indicated. By the 1970s and 1980s, astronomers had assembled a reasonably complete picture of the Milky Way's large-scale structure. Our galaxy was a barred spiral, meaning it had a central elongated structure from which the spiral arms emerged. The entire system was roughly 100,000 light-years in diameter, contained somewhere between 100 and 400 billion stars, and was embedded in a much larger halo of dark matter that extended perhaps 10 times farther than the visible stars. But even these impressive numbers were about to be dwarfed by discoveries that would push the boundaries of galactic scale far beyond anything previously imagined. The key insight came from studying something that couldn't be seen at all: dark matter. Dark matter revealed itself through its gravitational effects on visible stars and gas. As astronomers mapped the motions of stars throughout the galaxy, they discovered something puzzling. Stars in the outer regions of the galactic disk were moving much faster than they should have been based on the gravitational pull of visible matter alone. According to the laws of physics, stars farther from the galactic center should orbit more slowly, just as planets farther from the Sun take longer to complete their orbits. But observations showed that stars throughout the galactic disk were moving at roughly the same speed, regardless of their distance from the center. The only way to explain this observation was if there was much more mass in the galaxy than could be seen. Some form of invisible matter had to be providing the additional gravitational pull needed to keep those outer stars moving so quickly. This invisible component became known as dark matter, and its discovery revealed that the Milky Way was far more massive than anyone had realized. Dark matter observations suggested that the visible stars and gas that astronomers had been mapping represented only a small fraction of the galaxy's total mass. The rest was dark matter, invisible to all forms of electromagnetic radiation, but detectable through its gravitational influence on everything around it. This discovery fundamentally changed how astronomers thought about galactic scale. The visible Milky Way, impressive as it was, turned out to be just the bright center of an enormous dark matter structure that extended far beyond the stellar disk. Recent estimates suggest that this dark matter halo might extend up to nearly 2 million light-years in diameter, making the true Milky Way roughly 20 times larger than the visible galaxy. Think about what this means. When you look up at the night sky and see the ghostly band of the Milky Way stretching overhead, you're seeing only the innermost, brightest region of a structure so vast that its true boundaries lie far beyond anything visible to human eyes. We're not just inside a galaxy, we're embedded deep within a cosmic behemoth whose true scale dwarfs our wildest imaginations. But measuring this extended structure presents challenges that make earlier astronomical surveys seem simple by comparison. How do you map the distribution of something you can't see? How do you determine the boundaries of a dark matter halo that reveals itself only through subtle gravitational effects? Modern astronomers have developed ingenious techniques to tackle these problems. They study the motions of satellite galaxies orbiting the Milky Way, using their trajectories to map the gravitational field of our galaxy's dark matter halo. They analyze the orbits of globular clusters, ancient stellar systems that trace paths through the outer reaches of galactic space. They even study streams of stars that have been torn away from disrupted satellite galaxies, using these stellar debris trails as probes of the dark matter distribution. Each of these techniques provides a different piece of the puzzle, and combining them has revealed a galaxy of staggering complexity and scale. The Milky Way isn't just big, it's a multi-layered cosmic ecosystem with distinct regions, each playing a different role in the galaxy's overall structure and evolution. At the very center lies Sagittarius A, a supermassive black hole containing more than 4 million times the mass of our Sun. This gravitational monster sits at the heart of a central bulge, a roughly spherical region packed with old, red stars that formed during the galaxy's youth billions of years ago. Surrounding the central bulge is the galactic disk, the flattened region where most of the galaxy's star formation takes place. This disk is where we find ourselves, nestled within one of the spiral arms, about 26,000 light-years from the galactic center. The disk itself has structure, with distinct spiral arms that wind outward from the central bar, creating the elegant patterns that radio telescopes first revealed decades ago. But even the disk has hidden complexity. It's not a simple, uniform structure, but rather a dynamic system where gas flows inward and outward, where spiral density waves trigger star formation, and where stellar associations form and disperse over millions of years. The disk is also warped, twisted out of a perfect plane by gravitational interactions with satellite galaxies and the dark matter halo itself. Beyond the stellar disk lies the galactic halo, a roughly spherical region containing globular clusters, ancient stellar streams, and the vast majority of the galaxy's dark matter. This halo extends far beyond the visible stars, potentially reaching distances where the Milky Way's gravitational influence begins to overlap with that of our nearest large neighbour, the Andromeda galaxy. Recent observations have pushed our understanding of galactic scale even further. Advanced surveys using telescopes like the Gaia spacecraft have revealed stars and stellar streams at distances that were once thought to mark the absolute edge of the galaxy. These discoveries suggest that the Milky Way's stellar content extends much farther than previously believed, with some stars found at distances exceeding 300,000 light-years from the galactic center. But perhaps the most mind-bending aspect of measuring the Milky Way's size is confronting the question of where it actually ends. Galaxies don't have sharp boundaries like planets or stars. Instead, they fade gradually into the surrounding space, with their density dropping off slowly with distance until it becomes indistinguishable from the cosmic background. Different methods of measurement can give different answers depending on what you're trying to measure. Are you measuring the extent of the stellar disk, the reach of the dark matter halo, the distance to the last detectable star? Each approach yields a different number, and each number tells you something different about our galactic home. The stellar disk, where most of the galaxy's visible stars reside, extends roughly 50,000 to 60,000 light-years from the center in all directions, giving it a diameter of about 100,000 to 120,000 light-years. But recent observations have found stars much farther out, extending the known stellar content to distances of 200,000 light-years or more. The dark matter halo presents an even greater challenge. Current estimates suggest it might extend 300,000 to 400,000 light-years from the galactic center, giving the true Milky Way a diameter approaching 1 million light-years. Some theoretical models push this even further, suggesting the dark matter halo could extend up to nearly 2 million light-years in diameter. These numbers are so large they strain human comprehension. To put them in perspective, consider that light from the Sun takes about 8 minutes to reach Earth. Light from the nearest star beyond our Sun takes over 4 years to arrive, but light from the far side of the Milky Way's dark matter halo could take nearly 2 million years to reach us, meaning we're seeing those regions as they existed when our earliest human ancestors were just beginning to walk upright on the African savanna. The challenge of measuring such vast scales from our position embedded within the galaxy continues to drive astronomical innovation. New surveys are mapping billions of stars with unprecedented precision, revealing subtle patterns in stellar motion that provide clues about galactic structure and mass distribution. Space-based telescopes like Gaia have revolutionized our ability to measure stellar positions and motions, providing data that allows astronomers to trace the gravitational field of the galaxy with remarkable detail. Ground-based surveys are finding new satellite galaxies and stellar streams that serve as probes of the outer galaxy's structure. Future instruments promise even more dramatic advances. Next-generation telescopes will be able to detect individual stars in the galaxy's outer reaches, providing direct measurements of the stellar distribution at unprecedented distances. Advanced computational models are beginning to simulate entire galactic evolution, helping astronomers understand how structures like the Milky Way form and grow over cosmic time. But even as our measurements become more precise, fundamental questions about galactic scale remain unanswered. The exact extent of the dark matter halo is still uncertain. The total mass of the galaxy remains debated, with estimates ranging from less than 1 trillion to more than 2 trillion times the mass of our Sun. The number of stars in the galaxy could be anywhere from 100 billion to 400 billion, a range that reflects the difficulty of counting objects scattered across such vast distances. These uncertainties might seem frustrating, but they actually represent the exciting frontier of modern astronomy. We're living through a golden age of galactic discovery, where new observations regularly challenge our understanding and push the boundaries of what we thought we knew about our cosmic home. What makes this story even more remarkable is how these measurements have revealed that we're living inside a cosmic time machine. When astronomers peer toward the outer edges of our galaxy, they're not just looking across vast distances, they're looking back through time itself. The light from those distant stellar regions began its journey toward us millions of years ago, carrying information about what our galaxy looked like when mammoths still roamed the Earth. This temporal aspect of galactic observation adds another layer of complexity to understanding the Milky Way's true nature. We're not seeing a static snapshot of our galaxy as it exists today. Instead, we're observing a composite image built from light that left different regions at different times throughout history. The stars we see near the galactic center show us what that region looked like 26,000 years ago, while the most distant stellar streams might be showing us conditions from millions of years in the past. But perhaps the most mind-bending realization is that our measurements have revealed the Milky Way to be a dynamic, evolving structure, rather than a static collection of stars. Advanced computer simulations, fed with observational data from surveys like Gaia, show our galaxy as a living system where stars migrate between spiral arms, where gas flows in complex patterns from the outer regions toward the center, and where the entire structure slowly rotates like a cosmic pinwheel over hundreds of millions of years. The spiral arms themselves aren't permanent features, but rather density waves that sweep through the galactic disk, compressing gas and triggering bursts of star formation as they pass. These arms appear and dissolve over cosmic timescales, meaning the elegant spiral structure we see today is just a temporary pattern in the galaxy's long evolutionary story. This dynamic view has transformed our understanding of our own solar system's journey through galactic space. Our sun doesn't follow a simple, circular orbit around the galactic center. Instead, it traces a complex path that carries us in and out of spiral arms, through regions of varying stellar density and cosmic radiation levels. Over the past few billion years, our solar system has completed roughly 20 orbits around the galaxy, experiencing dramatically different cosmic environments as it traveled. Some researchers have suggested that this galactic journey might have influenced the evolution of life on Earth. As our solar system passes through spiral arms, it encounters higher levels of cosmic radiation and gravitational disturbances that could trigger climate changes or even mass extinctions. The timing of some geological events appears to correlate with our passage through these galactic features, though the connections remain hotly debated among scientists. The scale of our galactic motion is almost incomprehensible. Right now, as you watch this video, you're racing through space at over 500,000 miles per hour as part of the solar system's orbit around the galactic center. That's fast enough to circle the entire Earth in less than 5 minutes. Yet at this tremendous speed, it still takes our solar system roughly 225 million years to complete one orbit around the galaxy. To put this in perspective, the last time our solar system was in its current position relative to the galactic center, dinosaurs had not yet appeared on Earth. The next time we return to this same galactic location, our sun will be significantly older and dimmer, and life on Earth, if it still exists, will have evolved in ways we cannot possibly imagine. But our measurements have revealed that the Milky Way's story extends far beyond its current structure. The galaxy we see today is the result of billions of years of cosmic evolution, shaped by collisions with smaller galaxies, interactions with dark matter, and the complex physics of star formation and stellar death. Archaeological evidence of this history is written in the stars themselves. Different stellar populations throughout the galaxy tell the story of different epochs in galactic evolution. The oldest stars, found primarily in the central bulge and outer halo, formed when the galaxy was young and contained almost no elements heavier than hydrogen and helium. These ancient suns are cosmic fossils, preserving information about conditions that existed more than 10 billion years ago. Younger stellar populations, including our own sun, formed from gas that had been enriched by generations of previous stars. The elements that make up our planet and our bodies, carbon, oxygen, iron, and dozens of others, were forged in the nuclear furnaces of stars that lived and died long before our solar system was born. We are quite literally made of star stuff, assembled from atoms that have been recycling through the galaxy for billions of years. This cosmic recycling process continues today throughout the galaxy's spiral arms, where massive stars live fast and die young in spectacular supernova explosions that scatter their nuclear products into space. These stellar deaths seed the interstellar medium with the heavy elements needed to form new generations of stars and planets, ensuring that the galaxy continues to evolve and increase in chemical complexity over time. Recent observations have also revealed that the Milky Way is not an isolated island in space, but part of a complex cosmic ecosystem. Our galaxy is surrounded by dozens of smaller satellite galaxies including the famous Large and Small Magellanic Clouds visible from Earth's southern hemisphere. These satellites are gradually being torn apart by the Milky Way's gravitational field, their stars stripped away to form long streams that wrap around our galaxy like cosmic ribbons. Some of these stellar streams can be traced for hundreds of thousands of light years, providing astronomers with sensitive probes of the galaxy's gravitational field and dark matter distribution. The distortions and gaps in these streams reveal the presence of massive dark matter clumps that would otherwise be completely invisible. But perhaps the most dramatic example of galactic interaction lies in our future rather than our past. Advanced measurements of the motion of nearby galaxies have revealed that the Milky Way is on a collision course with its nearest large neighbour, the Andromeda galaxy. Currently separated by about 2.5 million light-years, these two galactic giants are approaching each other at roughly 250,000 miles per hour in approximately 4.5 billion years. Long before our Sun exhausts its nuclear fuel, the Milky Way and Andromeda will begin a cosmic dance that will fundamentally reshape both galaxies. Computer simulations of this future collision show a process that unfolds over hundreds of millions of years as the two galaxies pass through each other, their gravitational fields stirring stellar populations and triggering massive bursts of star formation. The final result will be a single, much larger galaxy that astronomers have playfully dubbed Milkomeda. This future galaxy will be roughly elliptical in shape rather than the elegant spiral structure we see today, and it will contain the combined stellar populations of both current galaxies, roughly 1 trillion stars in total. Remarkably, despite the violent-sounding nature of this galactic collision, the vast distances between individual stars mean that direct stellar collisions will be extremely rare. Our Sun and solar system will likely survive the merger intact, though they may be flung into a very different region of the combined galaxy. This future collision provides crucial context for understanding the true scale of our current galactic home. The Milky Way, enormous as it is, represents just one component of an even larger gravitational system that includes Andromeda and dozens of smaller galaxies scattered throughout what astronomers call the local group. The local group itself spans roughly 10 million light-years in diameter, making it about 10 times larger than the Milky Way's dark matter halo. Within this vast region, the Milky Way and Andromeda are the dominant gravitational players, with their combined mass accounting for the majority of normal matter in our local cosmic neighbourhood. But even the local group is just a small part of an even larger structure called the local supercluster, or Virgo supercluster, which contains thousands of galaxies spread across a region roughly 110 million light-years in diameter. Recent discoveries have revealed that this supercluster is itself part of an even more enormous structure called Laniakea, a gravitational basin containing over 100,000 galaxies across a region spanning 520 million light-years. These nested scales of cosmic structure provide important context for understanding what it means to measure the size of the Milky Way. Our galaxy, vast as it appears from our embedded perspective, is actually quite typical in the broader cosmic census. Most spiral galaxies fall within a similar size range, with diameters between 50,000 and 200,000 light-years. The Andromeda galaxy, our future collision partner, is somewhat larger than the Milky Way, with a stellar disk spanning roughly 220,000 light-years in diameter. Some galaxies are truly enormous, with the largest known spirals exceeding 500,000 light-years across. At the other extreme, dwarf galaxies can be as small as a few thousand light-years in diameter, containing just a few billion stars. These comparisons help put the Milky Way's scale in cosmic perspective. We live in a galaxy that is large enough to be interesting and complex, but not so large as to be unusual. Our cosmic home represents a kind of galactic middle ground, big enough to support the rich chemical evolution needed for planets and life. but not so massive as to be dominated by the violent processes that characterize the universe's largest galaxies. The ongoing refinement of galactic measurements continues to reveal new surprises about our cosmic neighborhood. Advanced surveys are discovering previously unknown stellar populations in the galaxy's outer regions, satellite galaxies so faint they were invisible to earlier searches, and complex structures in the dark matter halo that challenge our understanding of how galaxies form and evolve. One particularly intriguing recent discovery is evidence that the Milky Way's disk might be significantly warped, twisted out of a flat plane by gravitational interactions with satellite galaxies and the dark matter halo. This warping appears to be a dynamic phenomenon, changing over timescales of hundreds of millions of years as the galaxy responds to gravitational perturbations from its cosmic environment. The implications of this discovery extend far beyond simple geometric curiosity. A warped galactic disk affects stellar orbits, gas flows, and star formation patterns throughout the galaxy. It suggests that our cosmic home is more dynamic and responsive to external influences than previously thought, constantly reshaping itself in response to the gravitational environment of the local group. These ongoing discoveries underscore a fundamental truth about measuring the Milky Way's size. We're not just measuring a static object, but attempting to characterize a dynamic, evolving system that changes over timescales ranging from millions to billions of years. The galaxy we measure today is different from the galaxy that existed when the first stars formed, and it will be different again when our sun reaches the end of its life billions of years in the future. Future observational programs promise to push our understanding of galactic scale even further. Next-generation telescopes will be able to detect individual red giant stars throughout the local group, providing direct measurements of galactic structure at unprecedented distances. Advanced astrometric missions will map stellar motions with such precision that they can detect the subtle gravitational influences of dark matter clumps throughout the galactic halo. Perhaps most excitingly, the ongoing revolution in computational astrophysics is beginning to provide theoretical frameworks that can match the complexity of observational data. Modern galaxy simulations can follow the evolution of systems like the Milky Way from their formation in the early universe, through billions of years of cosmic evolution, predicting how galaxies grow, merge, and change over time. These simulations are revealing that galaxies like the Milky Way are not isolated objects, but products of a cosmic web of dark matter that spans the observable universe. The scale we measure for our galaxy today reflects not just local physics, but the entire history of cosmic structure formation, stretching back to the first moments after the Big Bang. In this context, measuring the size of the Milky Way becomes more than just an exercise in astronomical bookkeeping. It represents humanity's attempt to understand our place in a cosmic story that spans scales from subatomic particles to structures larger than we can directly observe. Every refinement in our measurements, every new discovery about galactic structure, adds another piece to the puzzle of how the universe creates and sustains the complex systems that make life possible. The numbers themselves, impressive as they are, tell only part of the story. The Milky Way's diameter of 100,000 to 200,000 light-years, its mass of 1 to 2 trillion solar masses, its population of 100 to 400 billion stars. These figures represent the quantified expression of a cosmic environment so rich and complex that it has produced not just stars and planets, but chemistry, biology, and ultimately, consciousness itself. We are the universe's way of measuring itself. Conscious beings evolved from stellar debris who have learned to map the very galaxy that gave birth to the elements of our bodies and the energy that powers our thoughts. In attempting to measure the Milky Way's true scale, we are engaged in an act of cosmic self-discovery, learning about our origins and our place in a universe far stranger and more wonderful than our ancestors could have imagined. The story of measuring our galaxy's size is ultimately the story of humanity's expanding cosmic perspective, from ancient myths about rivers of light in the sky to modern measurements of dark matter halos spanning nearly 2 million light-years. Each generation of astronomers has pushed the boundaries of the known a little further, revealing layer after layer of complexity and scale that continues to challenge our understanding and inspire our sense of wonder. As we stand on the threshold of truly comprehending our galaxy's magnitude, we must confront a humbling reality that fundamentally challenges everything we thought we knew about cosmic measurements. The numbers we've discussed, staggering as they are, represent only the beginning of a story so vast that it stretches the very limits of human imagination. Consider this perspective-shattering fact. If you could somehow shrink our entire solar system down to the size of a single grain of sand, the Milky Way galaxy would still span an area larger than the continental United States. That's the scale we're dealing with when we attempt to measure our cosmic home from the inside. But here's where the story takes a turn that should make every fibre of your being tingle with cosmic vertigo. Recent breakthroughs in observational astronomy have revealed that everything we thought we knew about the Milky Way's size might be dramatically underestimated. We're not just living inside a large galaxy, we might be inhabitants of a cosmic colossus whose true boundaries extend so far into space that they approach the realm of the genuinely incomprehensible. The key to this revelation lies in understanding what astronomers call the galaxy's dark matter halo. While the visible stars that paint those gorgeous spiral arms represent what we can see, they account for less than 5% of our galaxy's total mass. The rest is dark matter, an invisible form of matter that reveals itself only through its gravitational effects on everything around it. Imagine trying to understand the size of an enormous city at night, but the only lights you can see are scattered street lamps, representing a tiny fraction of the actual buildings and infrastructure. That's essentially what astronomers have been doing for decades when measuring the Milky Way. They've been mapping the street lamps, while the vast majority of the cosmic architecture remained hidden in darkness. Advanced computer simulations, fed with data from gravitational studies of satellite galaxies and stellar streams, now suggest that our galaxy's dark matter halo extends far beyond anything previously imagined. We're talking about a structure that might reach outward for nearly 1 million light-years from the galactic center, giving the true Milky Way a diameter approaching 2 million light-years. To put this in perspective, light from the outer edges of this dark matter halo began its journey toward us when our earliest human ancestors were just learning to control fire. The photons reaching your eyes right now from those distant regions carry information about galactic conditions that existed when saber-toothed cats still prowled the Earth. But measuring these invisible boundaries requires detective work of the highest order. Astronomers have become cosmic archaeologists, studying the debris trails left by satellite galaxies that have been torn apart by the Milky Way's gravitational field. These stellar streams, some stretching for hundreds of thousands of light-years, act like cosmic measuring tapes that reveal the true extent of our galaxy's gravitational influence. One particularly dramatic example is the Sagittarius stream, a river of stars that wraps around our galaxy multiple times like cosmic ribbon. This stream represents the remains of a dwarf galaxy that has been slowly shredded by the Milky Way's gravitational forces over hundreds of millions of years. By tracing the stream's path and measuring the distortions in its structure, astronomers can map the distribution of dark matter throughout our galaxy's outer regions. The implications of these measurements extend far beyond simple cosmic bookkeeping. If the Milky Way's dark matter halo truly extends for nearly 2 million light-years, then our galaxy is not just large, it's approaching the scale of galactic superclusters. We would be living inside a structure so vast that it challenges traditional definitions of what constitutes a single galaxy versus a collection of gravitationally bound systems. This expanded scale also fundamentally changes how we understand our galaxy's relationship with its neighbours. The Andromeda galaxy, our nearest large companion, sits roughly 2.5 million light-years away. But if both the Milky Way and Andromeda possess dark matter halos approaching 1 million light-years in radius, then these halos might already be touching or overlapping in the space between the two galaxies. This realization transforms our understanding of the future collision between the Milky Way and Andromeda. Rather than two discrete objects approaching each other across empty space, we might already be part of a single, enormous gravitational system that spans the entire local group. The collision we expect in 4.5 billion years might be more accurately described as the final merger of two components that have been gravitationally interacting for billions of years already. But perhaps the most mind-bending aspect of these new measurements is what they reveal about the nature of galactic boundaries. Where exactly does the Milky Way end and intergalactic space begin? The answer depends entirely on how you define the question. The visible stellar disk, where most of the galaxy's stars reside, has relatively well-defined edges at roughly 50,000 to 60,000 light-years from the centre. Beyond this lies an extended stellar halo containing globular clusters and scattered field stars that can be traced out to distances of 200,000 to 300,000 light-years. But the dark matter halo presents a fundamentally different challenge. Dark matter doesn't have sharp boundaries like the edge of a planet or the surface of a star. Instead, it fades gradually into the surrounding cosmic web, its density dropping off slowly with distance until it becomes indistinguishable from the background dark matter that fills the universe. Different theoretical models predict different cutoff distances for where the Milky Way's dark matter halo ends and the general cosmic dark matter begins. Some models suggest a relatively compact halo extending 300,000 to 400,000 light-years from the centre. Others predict a much more extended structure, reaching nearly 1 million light-years or more. The uncertainty in these measurements reflects one of the most profound challenges in modern astronomy. How do you measure the size of something when you can't directly observe most of its mass? It's like trying to determine the size of an invisible elephant by studying the footprints it leaves in mud. Recent observations from the Gaia spacecraft have revolutionized our ability to tackle this challenge. Gaia has measured the positions and motions of more than 1 billion stars with unprecedented precision, creating the most detailed map of galactic structure ever assembled. This data reveals subtle patterns in stellar motion that provide clues about the distribution of dark matter throughout the galaxy. One particularly intriguing discovery from Gaia data is evidence that the Milky Way's stellar disk is not perfectly flat, but instead exhibits complex warping and vertical structure. The outer regions of the disk appear to be twisted and flared, creating a three-dimensional shape that resembles a potato chip more than a flat pancake. This warping might be caused by gravitational interactions with the galaxy's dark matter halo or by the influence of satellite galaxies like the Large and Small Magellanic Clouds. The discovery suggests that our galaxy is a much more dynamic and responsive system than previously thought, constantly reshaping itself in response to gravitational forces from its cosmic environment. The warped structure also affects how we measure the galaxy's size. If the stellar disk is twisted and flared rather than flat, then its effective diameter varies depending on which direction you measure and at what height above or below the galactic plane you make your observations. These complexities illustrate why measuring the Milky Way's size remains one of astronomy's most challenging problems. We're not dealing with a simple geometric object with well-defined boundaries, but rather a complex dynamic system whose structure varies with time and whose extent depends on what components you choose to measure. Modern astronomical surveys are pushing these measurements to ever greater precision and distance. Projects like the Dark Energy Survey and the upcoming Legacy Survey of Space and Time will map stellar populations throughout the local group. potentially detecting individual bright stars in even the most distant satellite galaxies. These future observations promise to resolve many of the current uncertainties about galactic scale. They will provide direct measurements of stellar populations at unprecedented distances, allowing astronomers to trace the galaxy's structure far beyond the reach of current surveys. But perhaps more importantly, they will help answer fundamental questions about how galaxies like the Milky Way fit into the broader cosmic web. Are we typical examples of galactic structure, or do we represent some unusual configuration that makes us particularly difficult to measure from the inside? Recent studies comparing the Milky Way to other similar galaxies have revealed both similarities and differences that provide crucial context for understanding our measurements. The Milky Way appears to be a fairly typical spiral galaxy in terms of its stellar mass and star formation rate, but it might be somewhat unusual in having such a large population of satellite galaxies. The local group contains more than 80 known galaxies, most of them small dwarf systems orbiting either the Milky Way or Andromeda. This rich satellite population provides astronomers with numerous probes of our galaxy's outer structure, but it also creates a complex gravitational environment that might affect the galaxy's overall shape and size. Comparative studies with other galaxies suggest that the Milky Way's dark matter halo is probably similar in size to those of other spiral galaxies with comparable stellar masses. This provides some confidence that the extreme size estimates approaching 2 million light-years in diameter might be overestimates, with the true extent likely falling somewhere in the range of 600,000 to 1 million light-years. But even these more conservative estimates represent a galaxy of staggering scale. A dark matter halo extending 500,000 light-years from the center would give the Milky Way a total diameter of 1 million light-years, making it roughly 10 times larger than the visible stellar disk that astronomers have traditionally used to define galactic size. This expanded scale has profound implications for understanding galactic evolution and the formation of structure in the universe. A galaxy with such an extensive dark matter halo would be capable of gravitationally influencing its environment over vast distances, potentially affecting the formation and evolution of nearby galaxies and the overall structure of the local group. The measurements also provide crucial tests of our understanding of dark matter itself. Different theories about the nature of dark matter predict different distributions and extents for galactic halos. By precisely measuring the Milky Way's dark matter distribution, astronomers can test these theories and potentially learn about the fundamental physics of this mysterious cosmic component. Recent advances in computational cosmology have produced sophisticated simulations of galaxy formation that can predict the expected properties of systems like the Milky Way. These simulations suggest that galaxies similar to ours should indeed possess extended dark matter halos reaching hundreds of thousands of light-years from their centers. The simulations also reveal that these halos are not smooth spherical structures, but rather complex systems with substructure, streams, and irregularities created by the ongoing accretion of smaller systems. This predicted complexity matches many of the observational features detected in studies of the Milky Way's outer regions. But perhaps the most exciting aspect of these new measurements is what they suggest about the prevalence of large-scale structure throughout the universe. If typical spiral galaxies possess dark matter halos extending nearly 1 million light-years in diameter, then the universe might be more highly structured on large scales than previously thought. Galaxy halos of this size would overlap significantly with their neighbors, creating a cosmic web of gravitational interactions that spans vast regions of space. The boundaries between individual galaxies become blurred when their dark matter halos extend so far that they merge with the halos of nearby systems. This perspective transforms our understanding of galactic isolation. Rather than discrete island universes separated by empty space, galaxies might be better understood as dense nodes in a continuous web of dark matter that extends throughout the cosmos. The implications extend to our understanding of cosmic evolution as well. If galaxies possess such extended dark matter halos, then interactions between neighbouring systems begin much earlier and proceed much more gradually than traditional models suggested. The Milky Way and Andromeda might have been influencing each other's evolution for billions of years already, long before their stellar disks show obvious signs of distortion. These revelations about galactic scale also provide new context for understanding our own cosmic significance. We often think of Earth as a tiny speck in an enormous galaxy, but the true picture is even more humbling. Our entire solar system, vast as it seems from our terrestrial perspective, occupies a region of space so small compared to the galaxy's dark matter halo that it would be invisible even in the most detailed cosmic maps. Yet this humbling perspective also contains an element of profound connection. The dark matter that extends the Milky Way's boundaries far into intergalactic space is the same mysterious substance that helped form the cosmic web from which our galaxy condensed billions of years ago. We are not separate from this vast structure, but intimately connected to it through billions of years of cosmic evolution. The atoms that make up our bodies were forged in stellar cores throughout the galaxy's history, then scattered by supernova and stellar winds, before eventually finding their way into the molecular clouds that gave birth to our solar system. In a very real sense, we are products of the galaxy's entire evolutionary history, built from materials that have travelled vast distances through the galactic disk over billions of years. This cosmic recycling process continues today throughout the Milky Way's spiral arms, where massive stars live brief but spectacular lives before returning their nuclear products to the interstellar medium. The galaxy maintains its chemical richness through this ongoing cycle of stellar birth and death, ensuring that each new generation of stars and planets has access to the full periodic table of elements. The scale of this recycling process is matched by the scale of the galaxy itself. Material ejected by a supernova explosion in one spiral arm might drift through space for millions of years before being incorporated into new stars forming in a completely different region of the galactic disk. The galaxy's immense size ensures that this cosmic recycling operates on timescales that dwarf human history. But measuring the true extent of these processes requires understanding not just the galaxy's current structure, but its evolution over cosmic time. The Milky Way we observe today is the product of billions of years of growth through the accretion of smaller galaxies, the gradual settling of gas into a rotating disk, and the complex interplay between star formation and stellar feedback. Archaeological evidence of this history is preserved in the different stellar populations found throughout the galaxy. The oldest stars, with ages approaching the age of the universe itself, are found primarily in the central bulge and outer halo. These ancient suns formed when the galaxy was young and chaotic, before the elegant spiral structure we see today had time to develop. Intermediate age stars, including our own sun, formed after the galaxy had settled into a more organized configuration, but while significant star formation was still occurring throughout the disk. These stars show the chemical signatures of previous generations of stellar evolution, with heavier elements created by earlier supernova incorporated into their atmospheres. The youngest stars, found primarily in the spiral arms and star-forming regions, represent the current generation of stellar birth. These stars are the most chemically enriched, containing the full complement of heavy elements produced by billions of years of galactic chemical evolution. This stellar archaeology reveals that the Milky Way's current impressive scale developed gradually over cosmic time. The galaxy began as a much smaller, more chaotic system, and grew to its present size through the gradual accretion of material and the settling of gas into an organized, rotating disk. Computer simulations of galactic evolution suggests that systems like the Milky Way continue to grow throughout their lifetimes, gradually accreting material from the surrounding cosmic web. This ongoing growth means that the galaxy's size of this growth depends on the galaxy's environment, not fixed, but continues to increase slowly as cosmic time progresses. The rate galaxies in dense environments, wear, and the availability of material in the surrounding space. Neighboring systems compete for the isolated systems with same material might grow more slowly access to larger reservoirs of gas, and dark in the relatively sparse local group environment might have allowed it to grow to matter. The Milky Way's position, its current impressive size, without significant competition from nearby systems. This environmental factor could help explain why our galaxy appears to be somewhat larger than average for its stellar mass. Understanding this growth history is crucial for interpreting current measurements of galactic scale. The boundaries we measure today represent a snapshot of an ongoing evolutionary process that will continue for billions of years into the future. The Milky Way of tomorrow will be different from the galaxy we observe today, just as today's galaxy differs from the smaller, younger system that existed billions of years ago. These evolutionary considerations add another layer of complexity to the already challenging task of measuring galactic size. We're not just measuring a static object, but attempting to characterize a dynamic system whose properties change over timescales ranging from millions to billions of years. Future observations will need to account for this temporal complexity, using observations of stellar populations with different ages to reconstruct the galaxy's growth history and predict its future evolution. Advanced surveys like those planned for the next generation of space telescopes will provide the detailed stellar census needed to trace galactic evolution across cosmic time. But perhaps the most profound implication of these measurements is what they reveal about the nature of cosmic structure itself. The Milky Way, vast as it appears from our embedded perspective, is just one component of increasingly larger structures that extend throughout the observable universe. The local group, containing the Milky Way, Andromeda, and dozens of smaller galaxies, spans roughly 10 million light-years in diameter. This group is itself part of the larger Virgo supercluster, which contains thousands of galaxies spread across a region more than 100 million light-years in extent. Recent discoveries have revealed that even superclusters are part of even larger structures called galaxy filaments, vast chains of matter that can extend for hundreds of millions of light-years through space. These filaments are separated by enormous cosmic voids, regions of space that contain very few galaxies and appear nearly empty on the largest scales. This hierarchy of structure, from individual galaxies to superclusters to filaments, reflects the way matter organized itself under the influence of gravity over billions of years of cosmic evolution. The same gravitational processes that determine the size and structure of the Milky Way also shape the distribution of matter throughout the entire observable universe. Understanding our galaxy's place in this cosmic hierarchy provides crucial context for interpreting measurements of its size and structure. The Milky Way is not an isolated object, but rather a component of a vast web of matter that extends throughout space, connected to its cosmic environment through gravitational interactions that operate over enormous distances and timescales. These connections will become even more important in the future as the Milky Way continues to interact with its neighbours in the local group. The approaching collision with Andromeda represents just the most dramatic example of these ongoing interactions, but smaller scale encounters with satellite galaxies and cosmic gas streams will continue to shape our galaxy's evolution for billions of years to come. The final size and structure of the Milky Way will depend not just on its own internal dynamics, but on its interactions with the broader cosmic environment. Measuring the galaxy's current scale provides a baseline for understanding these future changes and predicting how our cosmic home will evolve over the remaining lifetime of the universe. In this context, Every improvement in our measurements of galactic scale contributes to a broader understanding of cosmic evolution and structure formation. The techniques developed to map the Milky Way's dark matter halo are being applied to other galaxies throughout the local group and beyond, building a comprehensive picture of how matter organizes itself on the largest scales. These measurements are also providing crucial tests of our fundamental theories of physics and cosmology. The distribution of dark matter in galaxies like the Milky Way provides constraints on the properties of dark matter particles and the processes that governed structure formation in the early universe. As our observational capabilities continue to improve, we can expect even more precise measurements of galactic scale and structure. Next-generation telescopes will push the boundaries of what we can observe, potentially detecting individual stars at distances that currently mark the limits of our surveys. Advanced computational models will provide increasingly sophisticated predictions for galactic structure and evolution, allowing astronomers to interpret observations in the context of our broader understanding of cosmic physics. The combination of better observations and improved theory promises to resolve many of the current uncertainties about galactic scale and structure. But perhaps most importantly, these measurements remind us of our intimate connection to the cosmos around us. We are not separate observers of galactic structure, but products of the very processes we're trying to understand. The galaxy's size and evolution directly influence the conditions that allowed our solar system to form and life to evolve on Earth. Every measurement of galactic scale is simultaneously a measurement of our cosmic heritage, revealing the vast scales of space and time that were necessary to create the conditions for our existence. In mapping the true extent of our galactic home, we're discovering the full scope of the cosmic story that led to our presence in the universe. The journey to understand the Milky Way's true size continues, driven by humanity's insatiable curiosity about our place in the cosmos. Each new measurement pushes the boundaries of the known a little farther, revealing layer after layer of cosmic complexity that challenges our understanding and expands our sense of wonder at the universe we inhabit. As we stand at the threshold of truly understanding our galactic home's magnificent scale, we must confront a reality that transforms everything we thought we knew about cosmic measurement. The techniques that revealed the Milky Way's structure have evolved from simple star counting to sophisticated space-based surveys that can track the motions of individual stars across vast galactic distances. The revolution began with the European Space Agency's Gaia mission, a space telescope that has fundamentally transformed our understanding of galactic architecture. Launched in 2013, Gaia has measured the precise positions and motions of over 1 billion stars, with accuracy so extraordinary that it can detect movement equivalent to watching a human hair grow from the distance of the moon. This unprecedented precision has revealed that our galaxy is far more dynamic and complex than anyone imagined. The Milky Way isn't a static collection of stars frozen in space, but rather a living, breathing cosmic organism where stellar populations flow like rivers through gravitational channels, where spiral arms pulse with waves of star formation, and where the entire structure rotates in a cosmic ballet that has been ongoing for billions of years. Gaia's measurements have shattered many of our previous assumptions about galactic structure. The data revealed that massive groups of stars are moving together through space in coherent streams, suggesting that our galaxy has been cannibalizing smaller neighbor galaxies for billions of years. These stellar streams wrap around the Milky Way like cosmic ribbons, each one telling the story of a dwarf galaxy that was torn apart by our galaxy's immense gravitational field. One of the most remarkable discoveries is evidence of what astronomers call galactic mergers. The Gaia data shows that roughly 10 billion years ago, the Milky Way collided with and absorbed a galaxy nearly 1/4 its size. This ancient collision, dubbed the Gaia-Enceladus merger, fundamentally reshaped our galaxy's structure and may have been responsible for creating the thick stellar disk and extended halo that we observe today. These findings illustrate just how challenging it is to measure something that's constantly changing and evolving. The galaxy we're trying to measure today is different from the galaxy that existed even a billion years ago, and it will continue transforming throughout its future evolution. We're not just measuring a structure, we're attempting to characterize a cosmic ecosystem that operates on timescales that dwarf human comprehension. The complexity becomes even more apparent when we consider the galaxy's three-dimensional structure. Modern observations have revealed that the Milky Way's disk isn't perfectly flat like a cosmic pancake, but rather exhibits complex warping and flaring that gives it a twisted propeller-like shape. This warping appears to be caused by gravitational interactions with the Large and Small Magellanic Clouds, our galaxy's most prominent satellite companions. The warped structure means that the galaxy's diameter varies significantly depending on where and how you measure it. In some directions, the stellar disk extends roughly 50,000 light-years from the center. In others, it reaches out to nearly 80,000 light-years or more. The galaxy's thickness also varies dramatically, from about 1,000 light-years in the outer regions to more than 12,000 light-years near the central bulge. But perhaps the most mind-bending aspect of measuring galactic scale is understanding how our solar system moves through this vast structure. Right now, as you absorb these words, you're racing through space at over 500,000 miles per hour as part of the solar system's orbit around the galactic center. Yet even at this tremendous velocity, it takes our solar system approximately 225 million years to complete one orbit around the galaxy. This galactic year provides a temporal framework for understanding cosmic scale that's almost impossible to comprehend. The last time our solar system occupied its current position relative to the galactic center, dinosaurs had not yet appeared on Earth. Complex life was just beginning to experiment with multicellular organization. The next time we return to this same galactic location, our sun will be noticeably older and dimmer, having consumed nearly 20% more of its hydrogen fuel. During our journey around the galaxy, we don't follow a simple circular path. Instead, our solar system traces a complex three-dimensional trajectory that carries us up and down through the galactic plane while we orbit the center. This motion means we periodically pass through the galaxy's spiral arms, encountering regions of higher stellar density, increased cosmic radiation, and enhanced gravitational disturbances. Some researchers have proposed that these passages through spiral arms might influence the evolution of life on Earth. The increased cosmic radiation and gravitational perturbations could trigger climate changes, affect the solar system's comet cloud, or even influence the rate of genetic mutations in terrestrial organisms. While these connections remain speculative, they illustrate how intimately connected we are to the galaxy's large-scale structure. The spiral arms themselves represent one of the most elegant features of galactic architecture, but they're also among the most difficult to measure accurately from our embedded perspective. Unlike the rigid spokes of a wheel, spiral arms are dynamic density waves that propagate through the galactic disk, compressing gas and triggering star formation as they pass. These spiral density waves travel around the galaxy at a different speed than the stars themselves, creating a pattern that persists even as individual stars move in and out of the arms over millions of years. The result is a structure that appears permanent when viewed from outside, but is actually a constantly changing pattern of enhanced star formation moving through the galactic disk. Current observations suggest the Milky Way has two major spiral arms, the Perseus and Scutum Centaurus arms, along with several smaller arm segments, including our own local Orion arm. But determining the exact number and structure of these arms remains challenging because dust absorption blocks our view of distant galactic regions, and our position within the disk makes it difficult to see the overall pattern. Radio astronomy has provided some of the clearest views of spiral structure by mapping the distribution of hydrogen gas throughout the galaxy. Hydrogen emits radio waves at a characteristic frequency that can penetrate dust clouds, allowing astronomers to trace the spiral pattern even in regions invisible to optical telescopes. These radio maps reveal elegant logarithmic spirals that wind outward from the galactic center with remarkable mathematical precision. But measuring the true extent of these spiral features pushes our observational capabilities to their limits. The outermost detectable spiral structures extend to distances of 60,000 to 70,000 light-years from the galactic center, but whether this represents the actual edge of the galaxy or simply the limit of what we can currently observe remains an open question. Recent discoveries have found isolated stars and stellar clusters at distances that far exceed the traditional boundaries of the galactic disk. Some of these objects lie more than 200,000 light-years from the galactic center, in regions where astronomers once thought the galaxy simply ended. These discoveries suggest that the Milky Way's stellar content extends much farther into space than previous surveys indicated. The challenge of defining where the galaxy actually ends becomes even more complex when we consider the different components that make up our cosmic home. The thin disk where most of the galaxy's gas and young stars reside has a relatively well-defined scale height of about 1,000 light-years. The thick disk, containing older stellar populations, extends roughly 3,000 to 4,000 light-years above and below the galactic plane. Beyond the stellar disks lies the galactic halo, a roughly spherical region containing globular clusters, ancient field stars, and the vast majority of the galaxy's dark matter. This halo extends far beyond the visible stellar components, potentially reaching distances of 300,000 to 400,000 light-years from the galactic center, though its exact boundaries remain poorly defined. The globular clusters that populate this halo serve as important tracers of galactic scale and structure. These ancient stellar systems, some containing over 1 million stars each, orbit the galaxy like celestial cities, following highly elliptical paths that carry them from the outer halo deep into the central regions. The most distant globular clusters provide direct measurements of the galaxy's gravitational influence at enormous distances. Studies of globular cluster orbits reveal that the Milky Way's gravitational field remains strong enough to bind these systems even at distances exceeding 200,000 light-years from the center. This suggests that the galaxy's total mass, including its dark matter component, extends at least this far into space. Some theoretical models predict that the gravitational influence could reach even farther, potentially extending halfway to the Andromeda galaxy. This brings us to one of the most profound questions in galactic astronomy. Where does the Milky Way end and intergalactic space begin? The answer depends entirely on how you define the boundaries of a galaxy. If you measure only the stellar disk, the Milky Way spans roughly 100,000 to 120,000 light-years in diameter. If you include the extended stellar halo, the diameter grows to perhaps 300,000 light-years. But if you consider the full dark matter halo, the galaxy might extend for 600,000 light-years or more in all directions. Different measurement techniques can yield dramatically different results, reflecting the complexity of defining boundaries for an object that doesn't have sharp edges. Unlike planets, which have well-defined surfaces, or stars, which have clear photospheres, galaxies fade gradually into the surrounding cosmic environment. The most conservative estimates, based on the distribution of easily detectable stars, place the Milky Way's diameter at approximately 100,000 light-years. This measurement has remained relatively stable for decades and represents what most astronomy textbooks cite as the galaxy's size, but this figure only captures the brightest, most easily observed stellar populations. More recent surveys, capable of detecting fainter stars and more distant stellar populations, have pushed these boundaries outward, significantly. The discovery of stars at distances exceeding 200,000 light-years suggests that the galaxy's stellar content extends at least twice as far as traditional measurements indicated. When we include theoretical predictions for the dark matter halo, the numbers become even more extreme. Computer simulations of galaxy formation suggest that dark matter halos around galaxies like the Milky Way should extend for several 100,000 light-years, with some models predicting extents approaching 1 million light-years from the galactic center. If these predictions are correct, the true Milky Way would have a diameter approaching 2 million light-years, making it roughly 20 times larger than the visible stellar disk. This would place our galaxy among the largest known structures in the local universe, rivaling the scale of galaxy groups and small clusters. But measuring these vast dark matter structures requires indirect techniques that push the boundaries of observational astronomy. Astronomers study the motions of satellite galaxies, analyze the distortions in stellar streams, and map the gravitational lensing effects produced by the galaxy's mass distribution. Each technique provides a different piece of the puzzle, but combining them to create a coherent picture of galactic scale remains one of astronomy's greatest challenges. The satellite galaxies orbiting the Milky Way provide particularly valuable probes of our galaxy's extended structure. The large and small Magellanic Clouds, visible to the naked eye from Earth's southern hemisphere, orbit at distances of roughly 160,000 and 200,000 light-years respectively. Their orbital motions reveal the strength of the Milky Way's gravitational field at these enormous distances. But the Magellanic Clouds are just the largest members of a vast population of satellite galaxies that surround the Milky Way. Recent surveys have identified more than 50 of these smaller companions, with new discoveries announced regularly as observational techniques improve. The most distant known satellites lie at distances exceeding 400,000 light-years from the galactic center. The orbits of these distant satellites provide crucial constraints on the total mass and extent of the Milky Way's dark matter halo. If the halo were significantly smaller than theoretical predictions suggest, these satellites would not remain gravitationally bound to our galaxy over cosmic timescales. Their continued presence implies that the Milky Way's gravitational influence extends at least as far as their current positions. But perhaps the most dramatic probe of galactic scale comes from studying stellar streams, the debris trails left behind when satellite galaxies are torn apart by the Milky Way's gravitational forces. These streams can extend for hundreds of thousands of light-years, wrapping around the galaxy multiple times like cosmic ribbons. The most famous example is the Sagittarius stream, created by the ongoing destruction of the Sagittarius dwarf elliptical galaxy. This stream completely encircles the Milky Way, with stellar debris detectable at distances exceeding 300,000 light-years from the galactic center. The stream's complex three-dimensional structure provides a detailed map of the galaxy's gravitational field throughout its outer regions. Studies of the Sagittarius stream and similar structures have revealed that the Milky Way's outer regions are filled with the debris of ancient galactic mergers. These stellar streams represent the archaeological record of our galaxy's growth history, preserving information about interactions that occurred billions of years ago. The complexity of this debris field illustrates just how active the Milky Way has been throughout its lifetime. Rather than growing smoothly through the gradual accretion of gas from the surrounding cosmic web, our galaxy appears to have assembled itself through the violent merger and disruption of smaller systems over billions of years. This hierarchical assembly process has profound implications for understanding galactic scale. The Milky Way we observe today is not a single primordial structure, but rather an amalgamation of hundreds or thousands of smaller systems that have been gravitationally captured and absorbed over cosmic time. Each merger event added mass to the galaxy and extended its boundaries farther into space. The cumulative effect of these interactions over billions of years has created the extended stellar halo and dark matter distribution that we observe today. In essence, the galaxy's current size reflects the entire history of its cosmic environment and the availability of smaller systems for accretion. This growth process continues today, as evidenced by the ongoing disruption of satellite galaxies like the Sagittarius system. The Milky Way is actively gaining mass and extending its boundaries through these interactions, meaning that measurements of galactic size represent snapshots of an ongoing evolutionary process. Predicting the galaxy's future size requires understanding not just its current structure, but also the population of nearby systems that might be accreted in the future. The local group contains dozens of smaller galaxies that could eventually be captured by either the Milky Way or Andromeda, adding to their masses and extending their boundaries even farther. But the most dramatic change in galactic scale will occur during the eventual collision between the Milky Way and Andromeda galaxy. Currently separated by roughly 2.5 million light-years, these two galactic giants are approaching each other at approximately 250,000 miles per hour. In roughly 4.5 billion years, they will begin a complex gravitational dance that will fundamentally reshape both systems. Computer simulations of this future collision reveal a process that unfolds over hundreds of millions of years. The two galaxies will pass through each other multiple times, their gravitational fields stirring stellar populations and triggering massive bursts of star formation. Gas clouds will collide and compress, creating conditions for the birth of billions of new stars. The final result will be a single, much larger galaxy that astronomers have dubbed Milky. This future system will contain the combined stellar populations of both current galaxies, roughly 1 trillion stars in total, making it one of the largest galaxies in the local cosmic neighborhood. Milky will likely be elliptical rather than spiral in shape, reflecting the violent nature of the merger process. The elegant spiral arms that define both current galaxies will be disrupted and destroyed, replaced by a more chaotic stellar distribution, typical of elliptical galaxies. The scale of this future galaxy will dwarf either current system. While the Milky Way and Andromeda currently span roughly 100,000 to 200,000 light-years each, Milky could extend for 400,000 light-years or more in diameter. The combined dark matter halos of the two galaxies will create an even more extended structure, potentially reaching across more than 1 million light-years of space. This future transformation provides important context for understanding current measurements of galactic scale. The Milky Way we observe today represents just one phase in a cosmic story that spans billions of years. The galaxy's current size and structure reflect its particular evolutionary history, but they also foreshadow dramatic changes that lie ahead. Understanding these future changes requires sophisticated computer models that can simulate galactic interactions across cosmic timescales. These simulations reveal that galaxy mergers are fundamental drivers of cosmic evolution, responsible for creating the largest and most massive galaxies in the universe. The Milky Way-Andromeda collision represents just one example of these cosmic interactions. Throughout the universe, galaxies are constantly merging and evolving, creating an ever-changing tapestry of cosmic structure. The techniques developed to study our own galaxy's merger history and future evolution are being applied to understand these processes on much larger scales. But perhaps the most profound implication of measuring the Milky Way's scale is what it reveals about our cosmic context. Every refinement in our understanding of galactic size places humanity in an ever-expanding hierarchy of cosmic structure that challenges our most basic assumptions about our place in the universe. We live on a planet orbiting an ordinary star located roughly halfway out from the center of a galaxy that spans hundreds of thousands of light-years and contains hundreds of billions of stars. This galaxy is itself just one member of a small group of galaxies that occupies a tiny corner of a much larger cosmic web extending throughout the observable universe. The numbers involved in these cosmic scales strain human comprehension. If you could somehow travel at the speed of light, the fastest possible speed in the universe, it would take you over 100,000 years just to cross from one side of the Milky Way to the other. To reach the Andromeda galaxy, you would need to maintain that impossible speed for more than 2.5 million years. These vast distances mean that when we observe distant parts of our own galaxy, we're seeing them as they existed in the past. Light from the galactic center shows us conditions that existed 26,000 years ago, when early humans were creating the first cave paintings. Light from the outer edges of the galactic halo carries information about stellar populations as they existed hundreds of thousands of years ago. In effect, every measurement of galactic scale is also a journey through cosmic time. The Milky Way we observe today is not a single, instantaneous snapshot, but rather a composite image built from light that has been traveling toward us for thousands or millions of years from different regions of the galaxy. This temporal aspect adds another layer of complexity to understanding galactic structure and evolution. The galaxy is not a static object frozen in time, but rather a dynamic system that changes continuously as stars are born and die, as gas flows through the spiral arms, and as gravitational interactions reshape the overall structure. Modern astronomy is beginning to capture this dynamic nature through time domain surveys that monitor millions of stars simultaneously, tracking changes in brightness, position, and motion over periods of years or decades. These observations reveal a galaxy in constant flux, with stellar explosions, planetary transits, and gravitational interactions creating an ever-changing cosmic landscape. The most ambitious future surveys will extend these time domain studies over much longer periods, potentially tracking galactic evolution over centuries or millennia. These observations will provide unprecedented insights into how galaxies like the Milky Way change over time, and how their measured properties reflect ongoing evolutionary processes. But even as our observational capabilities continue to advance, fundamental questions about galactic scale remain unanswered. The exact mass of the Milky Way is still uncertain by factors of 2 or more. The total number of stars could be anywhere from 100 billion to 400 billion. The extent of the dark matter halo remains poorly constrained, with estimates ranging from 300,000 light-years to nearly 2 million light-years. These uncertainties reflect not just the technical challenges of measuring cosmic scales, but also the fundamental complexity of defining what constitutes a galaxy. As our understanding of cosmic structure continues to evolve, so too does our conception of where the Milky Way ends and the broader universe begins. The boundaries we measure today may seem well defined, but they represent our current best understanding of a cosmic system that operates according to physical laws and processes that we're still discovering. Each new observation has the potential to revise our understanding of galactic scale, just as previous generations of astronomers repeatedly redefined the size and nature of our cosmic home. This ongoing process of discovery ensures that the story of measuring the Milky Way's scale will continue for generations to come. Future telescopes will push the boundaries of observation farther than ever before, potentially detecting individual stars throughout the local group and beyond. Advanced computational models will simulate galactic evolution with unprecedented detail and accuracy. Most importantly, these future discoveries will continue to expand our cosmic perspective, revealing new layers of complexity and beauty in the universe around us. The Milky Way, vast as it appears today, may prove to be just the beginning of a cosmic story whose true scale we're only beginning to comprehend. As we stand at the threshold of these future discoveries, we carry with us the accumulated wisdom of generations of astronomers who dedicated their lives to understanding our place in the cosmos. From ancient stargazers who first wondered about the nature of the Milky Way, to modern researchers using space-based telescopes to map dark matter halos, each generation has pushed the boundaries of the known a little farther. The measurements we've achieved represent humanity's greatest triumph in understanding cosmic scale. We've learned to see beyond the limitations of our earthbound perspective, to peer through cosmic dust and across vast distances, to detect the invisible influence of dark matter, and to reconstruct the history of our galaxy's formation and evolution. But perhaps the most remarkable aspect of this achievement is that it was accomplished by creatures who evolved on a small planet orbiting an ordinary star in an unremarkable region of galactic space. Through ingenuity, persistence, and an insatiable curiosity about the cosmos, we've managed to map the structure of our entire galactic home, despite being trapped within its boundaries. This accomplishment stands as testimony to the power of scientific inquiry and the remarkable capacity of conscious beings to understand their cosmic environment. In measuring the Milky Way's scale, we've not only learned about the universe around us, but also demonstrated our species' unique ability to transcend the limitations of our immediate environment through observation, reasoning, and imagination. The story of cosmic measurement continues, driven by the same curiosity that first led ancient astronomers to wonder about the nature of that ghostly band of light stretching across the night sky. Each new discovery adds another chapter to humanity's growing understanding of our place in a universe far stranger, more beautiful, and more vast than our ancestors could have dreamed. Tonight, as we reach the culmination of our cosmic journey through the Milky Way's immeasurable scale, we must confront a truth that will forever change how you perceive your place in the universe. Every number we've discussed, every measurement we've explored, every boundary we've attempted to define represents humanity's most audacious attempt to comprehend something so vast that it challenges the very nature of what it means to truly understand cosmic scale. But here's what should make your mind reel with wonder and perhaps a touch of cosmic vertigo. All of these measurements, all of this accumulated knowledge about our galactic home has been gathered by beings whose entire existence spans less than the time it takes light to travel from one edge of a single spiral arm to another. We are mayflies attempting to map eternity, yet somehow we've succeeded beyond our wildest dreams. Consider the profound irony of our situation. The in your bones, the iron in your blood, the oxygen, very atoms that make up your body, the calcium you breathe, all of it was forged in the nuclear furnaces of stars scattered throughout this vast galactic structure over billions of years. You are not separate from the Milky Way. You are the Milky Way, temporarily organized into a form capable of contemplating its own cosmic origins. This realization transforms our entire understanding of what it means to measure galactic scale. We're not external observers studying a distant object. We are the galaxy studying itself, matter organized into consciousness through billions of years of stellar alchemy and planetary evolution. Every telescope we build, every calculation we make, every moment of wonder we experience while contemplating cosmic distances represents the universe's attempt to understand its own structure through the temporary arrangements of matter we call human beings. The measurements we've achieved place us within a cosmic hierarchy so vast that it defies human intuition. Our solar system, which seemed enormous when we first began exploring it with spacecraft, occupies a region of space so tiny compared to the galactic disk that it would be invisible even in the most detailed maps of galactic structure. The distance from the Sun to Pluto, once considered the edge of our cosmic neighborhood, spans roughly 12 light hours. The Milky Way spans 100,000 light years. To put this in perspective, if you could shrink the entire solar system down to the size of a single cell in your body, the Milky Way would still be larger than North America. That's the scale we're dealing with when we attempt to comprehend our galactic home. Yet somehow, through centuries of patient observation and brilliant theoretical insights, we've managed to map this colossal structure with remarkable precision. The techniques that made these measurements possible represent some of humanity's greatest intellectual achievements. We've learned to use the parallax effect, measuring the tiny shifts in stellar positions as Earth orbits the Sun, to determine distances to nearby stars. We've discovered standard candles, objects whose intrinsic brightness we can calculate, allowing us to gauge distances throughout the galaxy. We've developed radio astronomy to peer through cosmic dust, revealing the elegant spiral structure hidden from optical telescopes. Perhaps most remarkably, we've learned to use the galaxy's own gravitational field as a cosmic laboratory. By studying the motions of stars, gas clouds, and satellite galaxies, we can map the distribution of matter throughout the Milky Way, including the invisible dark matter that comprises most of its mass. We've turned our galaxy into a vast experiment in gravitational physics, using stellar orbits to probe the fundamental structure of space and time. These achievements become even more extraordinary when you consider the observational challenges we've had to overcome. Imagine trying to map the layout of a vast city while blindfolded, located somewhere within its boundaries, with dust and fog obscuring your view in every direction. That's essentially what astronomers have been doing for centuries in their quest to understand galactic structure. The interstellar dust that fills the galactic disk absorbs and scatters light from distant stars, making them appear dimmer and redder than they actually are. This cosmic fog had been systematically distorting distance measurements for decades before astronomers learned to account for its effects. Even today, dust absorption remains one of the primary obstacles to observing the galaxy's most distant regions. But we've developed ingenious methods to overcome these limitations. Radio waves can penetrate dust clouds that completely block visible light, allowing us to map the distribution of hydrogen gas throughout the galaxy. Infrared telescopes can detect the heat radiation from dust grains themselves, revealing the structure of star-forming regions hidden from optical view. Space-based observatories eliminate the blurring effects of Earth's atmosphere, providing the precise measurements needed to detect stellar motions across vast galactic distances. Each technological breakthrough has pushed our understanding of galactic scale to new frontiers. The Hubble Space Telescope revolutionized our ability to measure distances to nearby galaxies, providing crucial context for understanding the Milky Way's place in the cosmic hierarchy. The Spitzer Space Telescope mapped the galaxy's infrared emission, revealing its true spiral structure for the first time. The Kepler mission, while searching for exoplanets, provided unprecedented data on stellar populations throughout our galactic neighborhood. But perhaps no single mission has transformed our understanding of galactic scale more dramatically than the European Space Agency's Gaia spacecraft. This remarkable observatory has measured the positions and motions of over 1 billion stars, with accuracy so extraordinary that it represents a quantum leap in our ability to map galactic structure. Gaia's precision is equivalent to measuring the width of a human hair from a distance of 1,000 kilometers. The data from Gaia has revealed that our galaxy is far more dynamic and complex than anyone imagined. Stars don't simply follow circular orbits around the galactic center, but instead trace complex three-dimensional paths that carry them through different regions of the galaxy over millions of years. Stellar streams wrap around the Milky Way like cosmic ribbons, preserving the archaeological record of ancient galactic mergers that occurred billions of years ago. These discoveries have forced astronomers to completely revise their understanding of how galaxies form and evolve. The Milky Way we observe today is not a primordial structure that formed fully assembled in the early universe. Instead, it represents the accumulated result of countless mergers and interactions with smaller galaxies over cosmic time. We live inside a cosmic recycling center where matter is constantly being reorganized and redistributed through gravitational processes operating over billions of years. This hierarchical assembly process explains many of the structural features we observe throughout the galaxy. The central bulge, packed with ancient red stars, formed during violent mergers in the galaxy's youth when smaller systems crashed together and stirred their stellar populations into a roughly spherical distribution. The thin disk, where most current star formation occurs, developed later as gas settled into a rotating configuration and began forming new generations of stars enriched with heavy elements from previous stellar generations. The thick disk, containing intermediate-age stellar populations, likely formed during a major merger event roughly 10 billion years ago when a substantial satellite galaxy was disrupted and its stars scattered throughout the Milky Way's inner regions. The extended stellar halo preserves the debris from countless smaller merger events, creating a complex three-dimensional structure that extends far beyond the visible galactic disk. Understanding this assembly history is crucial for interpreting current measurements of galactic scale because it reveals that the boundaries we observe today reflect the entire evolutionary history of our cosmic environment. The galaxy's current size depends not just on its initial formation conditions, but on the availability of smaller systems for accretion throughout cosmic time. This evolutionary perspective also provides important context for understanding our galaxy's future. The Milky Way continues to grow through ongoing interactions with satellite galaxies, and this growth will accelerate dramatically during the eventual collision with Andromeda. The merger will create a galaxy significantly larger than either current system, potentially spanning 400,000 light-years or more in diameter. But even more profound changes may lie further in the future. As the universe continues to expand and galaxy groups become increasingly isolated from each other, the local group will eventually become a closed system with no external sources of new material. At that point, galactic evolution will be driven primarily by internal processes, the gradual consumption of gas reserves through star formation, the evolution and death of stellar populations, and the slow redistribution of matter through gravitational interactions. Over truly cosmic timescales, measured in trillions of years, even these internal processes will run their course. Star formation will eventually cease as gas reserves are exhausted, and the galaxy will slowly fade as its stellar populations age and die. The final result will be a collection of stellar remnants, white dwarfs, neutron stars, and black holes, orbiting in the darkness of a universe that has expanded far beyond its current scale. These distant futures provide ultimate context for understanding the significance of our current measurements. We live during a brief golden age of galactic evolution when star formation continues actively, when spiral structure remains clearly defined, and when the galaxy maintains the elegant architecture that makes detailed observations possible. The measurements we achieve today document a cosmic structure at its peak of beauty and complexity. As we reach the end of our cosmic journey tonight, remember that every breath you take connects you to stellar nurseries billions of years old. The Milky Way isn't just our address in the universe, it's the cosmic story written in starlight and dark matter, spanning up to 2 million light-years of space and time. We've measured the unmeasurable from within, proving that curiosity and ingenuity can illuminate even the vastest cosmic mysteries. Keep looking up,